We're going to expand a little bit on today's labs and kind of lock down some concepts. Let's say we have a two-wheel car that starts down here at point A, and we want to get that car to point B. Now your initial instinct might be, okay, well our car should just drive in a straight line from point A to point B. That will be the fastest route. But it turns out that part of our travel will be in pavement where our car can go fast, and part will be in sand where our car can go slow. Even though we're trying to get from A to B, we're actually not going to drive in a straight line if we want to go our fastest possible. We want to reduce the amount of distance we cover in the sand because our car goes slow there. And so we will cover distance more slowly in the sand. We want to spend most of the distance we travel in the pavement because our car will go faster there. So we actually want to spend most of our angled time. So if you think about we have to travel at an angle to get from A to B, we want to spend most of our time and most of our angle, I guess I should say most of our distance and most of our angle in the fast pavement, because this is a longer distance here than if we just traveled straight up. But even though it's a longer distance, we can travel it really fast because we're in the pavement. And then we want to try to go as straight as possible in the sand, because the bigger the angle, the bigger the distance, and we're slow in sand, so we need to spend less of our distance in the sand. If we did it the other way, if we started out slow in the sand and went up to the pavement from A to B, we again want to spend most of that angle in the pavement, because the more angled our path is, the bigger the distance. An angled path is longer than a straight path, and you should know that from triangle geometry, that the hypotenuse, the angled side of the triangle, is the longest side. So we're going to go as straight as possible in the sand, and then get as much of our angle in that pavement as we can. The way we say this is that we go from fast to slow, so we went from fast to slow. We'll refract toward the normal. We'll bend because we're crossing between media. Now you might be confused about the normal. What we do is we draw just a dotted line that creates a right angle between the boundaries of the two media. So this is the boundary where they meet. And when you pass into a slow medium, you have to bend toward the normal, which means you're going to be covering less distance. So when you pass into the slow angle, slow media, you have a smaller angle with the normal. In the fast media, you had a bigger angle. If we go from the slow to the fast, we refract away from the normal, because the bigger the angle, the longer the distance. So small angle in the fast, small angle in the slow, small angle here, big angle in the fast pavement, big angle up here. Here's the rule to remember. Farther equals faster. When you're in the faster medium, you're farther from the normal. The ray is farther from the normal in the faster medium. That's kind of the easy way to remember it. You remember the opposite's true. Slower equals closer. Ray is closer to the normal in the slower medium. That's why some things like this happen. If you pass a laser beam through a glass, you'll see it bends inside there. Same thing with light. The reason this pencil looks kind of out of shape is that the light bent as it went through that medium because it was slower in the glass. So it traveled at a different angle to try to get through the glass as fast as possible. And same thing with a prism. It's how a prism is bending the light in one side and out the other and creating those angles. Okay, let's look at a couple of quick practical examples here. First off, a ray of monochromatic light, that means one color, monochromatic, of frequency 5.09 times 10 to the 14 hertz is traveling from water into medium X. So it goes from the water into medium X. The angle of incidence in the water is 45 degrees. The angle of refraction in the medium is 29 degrees. So by the way, whenever you're given Snell's law problems, the angle that you come in at is called your angle of incidence, sometimes labeled theta I. And the angle you leave at is called your angle of refraction, sometimes called theta R. Calculate the absolute index of refraction of medium X. Now, the only index of refraction I've shown you is the absolute. N equals speed of light over speed in the medium. And it's absolute because we consider the speed of light an absolute measure, so it's an absolute comparison. And this should be fairly straightforward. I'm calculating the index of refraction of medium X. So this is a Snell's law job because I've got the angles of incidence and the angles of refraction. So my incident index of refraction times sine of the incident angle is equal to the refracted index of refraction times sine of the refracted angle. So we start out with water, that would be Ni, and we're looking for Nr for medium x. So let's solve this equation by dividing by sine theta r, and I get Nr, also kind of switching the sides, flipping the equation around, equals Ni sine theta I divided by sine theta r. Then I just plug in the numbers. So Nr equals the index of refraction for water, which is 1.33. But that's a common one, and even though it would be given to you, I keep the index of refraction of water memorized just because it comes up so much, and so I don't have to bother like going back and reading to find out what it is. It saves a few minutes. Times sine of the incident angle over sine of the refracted angle. Okay, check my math, but when I do that out, I get that the refracted index, or for medium x, is 1.9-ish. And then the question says medium x is most likely what material? Now, this example is one that I found, and it's not a good starter example because 1.9 is not on our list. And so for the perfect, like, starting out with Snell's law, they're asking you to decide what material it is. You might want it to be easy so you can see that it's right. Since it's not on the list, though, we're going to pick the one that's closest. And if you pick the one that has the least difference from 1.9, it's flint glass. And so, most likely, is kind of your cue that you're going for the one that's closest. And the closest one is flint glass. The next closest might be diamond, but it's still farther off than flint glass. And so, that's how you could use like an index of refraction to figure out what some material is. You could look up like a table of common materials, and then whatever you get, pick the one that's closest. In actuality, if this were the results of a real experiment, I might say it's some combination of flint glass and diamond, because higher than flint glass but lower than diamond, so maybe you mix the two or something like that. But for the purposes of this or the AP exam, you pick the one that's closest. Okay, so let's move to our second example. A light ray with frequency 5.09 times 10 to the 14th hertz. They're really trying to see if you know what's important and what's not. Traveling in air is incident at an angle of 40 degrees. So they've got that drawn here for us. At the interface, part of the ray is refracted as it enters the water. And that's because some would reflect back, but we're not concerned about that right now. So it refracts as it enters the water, and part is reflected from the interface. Calculate the angle of refraction of the light ray as it enters the water. Well, that's a Snell's law problem, and I'm going to write it the way it was in your lab just for no confusion. So your first material was N1 sine theta 1. Sometimes it's helpful for me to say I and R, so I remember if I'm talking about the incident and refracted, or you can say 1 for the first one and 2 for the second one. No AP grader would care if you had labeled them R and I. Okay, so right now I'm looking at the angle of refraction, so that would be the angle in the second medium. So if I solve for that, first I'll divide by N2, and then I'll take the inverse sign. So step by step, divide by N2. Now I've got N1 sine theta 1 over N2 equals sine theta 2. And so I'll take the inverse sine of both sides to get theta by itself. And now I've got the inverse sine of N1 sine theta 1 over N2 equals theta 2. And then I can plug in the numbers. So it's the inverse sine of the index of refraction of air, which is about 1, but let's see if it's somewhere in our handy dandy chart. Air, they label as 1.00. So 1.00 times the sine of 40 degrees divided by N2, water. Now I told you I just carry that around in my head as 1.33 because it comes up so much, but our chart says 1.33 if I look back. right there, divided by 1.33. And if I do out that math, okay, and I got that theta 2 is about 29 degrees. I rounded there. On the ray diagram, using a protractor and straight edge, draw the refracted ray. So I'd actually need to take a protractor and measure out 29 degrees from here. Now this is impossibly hard on an iPad because I have to like set a bunch of stuff on top of it and then try to trace with this little stylus. But let's say I did grab a protractor. This turned out to be 29 degrees right there. Or not turned out, but that was 29 degrees. Then I might draw as straight as I can, and this is going to look terrible on here. Right there. On the AP exam, you're allowed to take in a ruler, and so it is quite possible you'll have a problem that asks you to find an angle and draw it. And if you didn't have a protractor, which I don't think you get to take, you would just maybe estimate the angle, but then your drawing should be much straighter than mine because they're going to know you're allowed to take in a ruler. And if you don't draw it straight, they'll know you were just being lazy. Alright, and then it says label this the refracted ray. Refracted ray. Also, on the diagram, using a protractor and straight edge, draw the reflected ray. Now, even though a lot of you had trouble with the mirror lab, your incident ray is always the same as your refracted ray. And if you just want to remember that as a rule, you can. Or you can play around with some lasers, or even like a little tennis ball and bounce it off the wall at some angle, and you'll see it bounces off at the same angle. So, I would draw it at the same angle. Again, I draw it with a protractor really carefully. Label that the reflected ray. So the key here, this surface, that reflection, since this is a flat surface, acts like a plane mirror, so a flat mirror. It just bounces off at the same angle. You can remember that rule. A plane mirror will always reflect a ray at the same angle it came in at. So your incidence and your reflected angle will always be the same for a plane mirror. And a plane mirror, P-L-A-N-E, just means a flat mirror. Okay, I have one last short example just because I think this is where there'll be a lot of confusion. Sketch the ray's path in the glass prism surrounded by a vacuum. And then that second part is for something that I deleted off here. So we've got a glass prism surrounded by a vacuum, labeled there, and an incident ray comes in. Now this is, if we were to draw a normal, that lines up with our normal. There is no angle between the ray and the normal. So if we were to do Snell's law, N1 sine theta 1 equals N2 sine theta 2, our sine theta 1 would be 0. And this entire side would be 0, equals N2 sine theta 2. No matter what we subbed in for N2, when we divided, we'd still get 0 equals sine theta. If you take the inverse sine of 0, it is 0. Now, the inverse cosine of 0 would actually give you something else. You can go try that with a calculator. But the inverse sine of 0 is 0. And so there is no refracted angle, so it passes straight through. You might be tempted to say, well, then won't it pass straight out? No, because you always measure at a 90 degree to your surface. So now I've got to draw a line that's 90 degrees to this surface. And so when my ray hits this surface, I've got to figure out what this angle is, and ideally that blue line would have hit the edge of my arrow. I was off a little bit there. Now I've got to figure out what the angle was there. What you might notice is that since this is a triangle inside of a bigger triangle, these are going to be similar triangles. So this would be the 90 degree angle. And then if you thought about the angles a little bit and tried to kind of calculate out, okay, if this one's 90 and this one's whatever, you could eventually get to this internal angle here is 30 degrees. Now, if you need to work through the geometry to convince yourself, great. If you want to stop by and have me work through it with you to convince you, great. But I don't want to make this video an hour long. So these are similar triangles, and whenever you have this particular situation, the angle right here will always be the same one as the one up here. And you could work through that, or you could take my word for it. I encourage you to work through it. Curiosity is the best. So that means that when our ray emerges, because a vacuum is a faster medium, and remember faster equals farther, should actually refract away a little bit. So a bigger angle out here, bigger than 30 degrees. Because our index of refraction for vacuum is exactly 1, and for glass it's something like 1.5, making glass the slower medium. So the bigger your index of refraction, the slower your medium. That's actually worth writing down. Bigger the index of refraction, the slower the medium. And earlier I told you faster equals farther, so if the vacuum is faster, our ray would bend farther away from the normal. And if we were to carry out the Snell's law calculation for this interaction right here, you would have to put in 30 degrees as your sine. For sine theta 1, you'd put theta 1 as 30 degrees, and you'd get out theta 2. The big takeaway here is, though, you're always measuring compared to a line normal to the surface. So you always have to make that right angle line, and when you're dealing with a triangular prism, that could be confusing. And you're going to have a couple of these tomorrow, and this showed up a few years ago on the AP exam. I think 1998, this very question was actually taken from. So you'll have stuff like this that you've got to be able to do. Alright, we'll practice a few more of these tomorrow. That last one might have been confusing, so you might want to rewind about 4 minutes to try this again. Otherwise, see you tomorrow.